Shoham, are you ready?
Yes, ma'am.
So we will start. It's almost 6.
Okay, ma'am. Okay, so good evening, everyone. I am Soham Bakchi from the first year of Physics Department, the Heritage College. I would like to thank all of you to attend for attending our seminar today, the Freshman Forum. Uh, I know this. I'm aware of the situations in the world right now. We are in very drastic conditions. So, thank you for taking time out of your busy schedule and attending our seminar. We appreciate it a lot. But first, before beginning our going forward with our seminar, I would like to call upon the professor in charge, Amitav Ghosh, to speak a few words.
Just a minute. Yes, am I audible?
Yes, sir, you are.
Good evening to all. Honorable Mr. Robbie Roy, Director of the Heritage Group of Institutions, Mr. Pradeep Agarwal, CEO of the Heritage Group of Institutions, Mr. Professor Bashok Chaudhuri, Senior Director, Higher Education of the Heritage Group and Principal of the HIT, Dr. Madhupata Bhattacharya, Head of the Physics Department, colleagues, friends, and beloved students. It's my pleasure to extend a warm welcome to everyone uh, for this student seminar. We in Heritage College are proud of the physics department. Going by the results of the physics department, it is one of the best in the city. The Heritage College is one of the few colleges in Bengal which is holding regular student seminar besides conducting regular classes. My heartfelt thanks to Dr. Madhupata Bhattacharya and her team for involving the mind and energy of the students in specialized subject areas. I have gone through the topics. I'm a layman in your area. I have just little knowledge about black hole and aerodynamics. Of course, my knowledge about aerodynamics was mainly inspired by my love for car. Whenever I buy a car, I look for its aerodynamics. And particularly, I look for the index which measures the aerodynamics. Whether it is 0.30, 0.31, that is only my interest in aerodynamics. Uh, of course, in India, we are very much concerned with fuel efficiency and stability at high speed. That's why we are interested in this topic. In any case, that is not my area. Uh, Now we have gone through an unprecedented period of crisis during the last 15 months. But every crisis brings new challenges and opportunities, thereby inducing reforms. We would have never used the digital platform to organize this kind of students' webinar had there been no pandemic. So we got the opportunity to experiment. I'm very confident that when we'll move from the new normal to old normal, we'll be able to make a novel and optimal mixing of offline and online platforms to plan our academic activities and also extracurricular activities. Now, without further delay, I will turn the time to the students for their seminar. Thank you once again. Thank you, madam. Thank you, the students, for organizing the seminar.
Thank you, sir, for those really kind words. I would like to call upon our HOD, Dr. Madhupata Bhattacharya, to share her thoughts now.
Respected Professor Amitabh Ghosh, my dear colleagues, respected guests, students, a very good evening to all. On behalf of the Heritage College, I feel privileged to welcome you all in this webinar organized by the Department of Physics. I am happy to announce that this year also my students have done a wonderful job. It is a webinar completely organized by them. Today we will have 19 excellent speakers under the supervision of 3 awesome mentors. I want to thank Vishal, Prutay and Manush for being my strength always. I would like to congratulate same 2 students as it is their first webinar, and I know students, you are going to make me proud again. Thank you.
Thank you, ma'am, for sharing your thoughts. Now, without further ado, I'd like to continue. But before we begin with the event, I think we need to lay a few ground rules. It's very simple. Just you need to keep in mind that you are to never turn on your camera or microphone throughout the entirety of this event. It only helps us in the smooth sailing. And if you have any queries regarding any presentation throughout the event, you can just put your queries down in the chat box. We will be keeping an active look on it and all your queries will be answered. But since the time is nigh and we are running low, we will try to answer as many questions as we can. And if we are not able to in the limited time, you will receive an answer response to your query in the chat box itself. So keep a lookout in the chat box. So basically do not turn on your camera or microphone throughout the entirety of this event. And I think that's very clear. So I would like to just move on. But I think you might all be asking a question like, why are we listening to a bunch of freshmen give us random lectures in various topics of physics anyway? Like, we certainly don't know more than most of you out here. And even if you are not from a physics background, you might be like, why I'm listening to physics anyway? Let me kind of tell you, I think I have a sort of an answer, and that is belongs to is that physics, I think, is the most philosophical of all sciences out there. Its early roots are in fact in ancient philosophy, when people finally decided to sit down and discuss about the larger, bigger aspects of life, like what is the meaning of life, or why are we here, what are we doing. And these are big questions that I think we all have asked ourselves at some point in our life. Like after 1 a.m. when you are sitting alone in your room, you have these thoughts. But for the most part, we just leave them behind because they are just too big for us to ask. We don't have a definite answer to any of them, and we just move on. But there are some people who decide not to. They are relentless in their pursuit of these answers. They want to know about the universe. They want to find some order to the unorderedness, even when it doesn't make any sense. And it is their work that has led us to this day. Physics is an avenue that a lot of those people have used to justify our existence in this universe. And it is their work and research that we are going to be discussing today. You might be thinking that it is just an accumulation of knowledge that has helped us in this field of study of physics, and that is it all just maths and formulas and equation. But I assure you that it's not. It's actually a lot filled with deep passion and curiosity that these people displayed that have led them here. And I assure you that whatever my classmates lack in their knowledge, they will make up for it in their passion and their curiosity for the subject. And they're prepared really hard. So I would ask you to keep an open mind and just listen. And I assure you, if not, you are entertained by the end of it, you will be engaged through the entirety and maybe gain a little more knowledge about our stream. Now, I know I talked about the big philosophical aspects of physics, but physics isn't just all big abstract ideas. It's a lot more. You can actually see physics all around us. in our day-to-day life, in all the technological advancements that are taking place. They all are based on some kind of physical law. Take the car, for example, a piece of daily machinery we all use. Like Professor Amitabh Ghosh said, he was a very into big car enthusiast. So, but the thing is, lot of us just buy cars and enjoy them for the look, but we don't question what goes behind the design of those looks. It is actually a very lengthy process, I must say, that takes a lot of research to design those distinct looks that those cars have. A family car looks much different to a racing car. And to answer why are those designs like the way they are, I love to call upon our first presenter today, Swarnava Das, with his presentation, Fast and Furious.
Good evening, respected professors, beloved friends and seniors. I am Sharnava Das and I will be speaking for the group Fast and Furious. It has been a long time since cars made their first appearance on road, and since then it has evolved in terms of technology, engines, and the most distinctive one, designs. In 21st century, we can easily look at a car and tell whether it is fast or not. Do the manufacturer, but why? Do the manufacturers design their car to look distinguishable, or they just want to look fast, or there is any deep reason behind it? Canards, spoilers, vents are some of the things that are gaining popularity in the modern car scene nowadays. Today I am going to discuss how all the manufacturers are trying to take advantage of one single thing, and that is none other than aerodynamics. Now, aerodynamics plays an important role when it comes to speed, performance, and handling. But what is aerodynamics? Aerodynamics is the study of forces and the resulting motion of objects through the air. The basic aerodynamic forces are drag and lift. Drag is the force that air exerts as a car moves. Lift is the perpendicular force exerted by the air on the car. Now, lift is of two types: positive lift and negative lift. Positive lift is the one which exerts perpendicular force upwards and makes the object to take off. Negative lift is none other than down force. Now, the air being a fluid, whenever we are driving, it is like we are swimming through an endless air ocean. And since we are driving against the air, it is causing friction, which results in drag. Now, drag is nothing but v squared times cd times a, where v is the drag velocity, cd is the drag coefficient, and a is the frontal area. Now, the drag coefficient depends on a number of factors such as the car's overall shape, surface roughness, and speed. For instance, the brake has an awful drag coefficient of 1, whereas a teardrop, being the most aerodynamic, has the drag coefficient of 0.05. Now, we don't have to worry much about drag at lower speed, and that is the main reason why the manufacturers in the earlier days didn't pay much attention to shapes, because the cruising speed at that time were barely up to 45. But the earlier land speed record holders quickly realized that streamlining their cars made it a way lot easier for them to go faster, because drag increases exponentially with speed and hence slowing the car down. Now, to understand drag better, let us consider a fast moving non-aerodynamic brake. Now, when a brake moves, the air piles in front of it to create a high pressure area, whereas behind it a low pressure pocket is formed, which results in pressure differential. And this pressure differential forces the brake to come backward, and that's how drag is formed. And drag is an important factor for determining the performance of a car. Now, you might be thinking that F1 cars, the pinnacle of motorsport history, might have extremely less drag coefficient because of their extreme speed, and they're even faster than jet planes on land. But you are wrong. F1 cars have drag coefficient of nearly about 0.7, which is even more than any conventional minivan. But why? F1 cars or any other sports car are designed with lift in mind because traction and grip is as important as speed and power for faster lap times. Now, the automotive engineers in the earlier days used to think that reducing the drag coefficient as much as possible would help them to get faster and become supreme than the other cars. But later they found that the sports cars started flying off, and later they realized that no, downforce is also important for the cars to complete the races at least. But a lot of downforce creates a lot of drag. But it has been proven that it is a worthy trade-off because the lateral grip produced from the downforce gives higher cornering speed. But what is creating the lift? Now let us take example of that same brick discussed previously with the high pressure in front and the low pressure at the back, which creates the pressure differential. Now in this case, the same thing occurs from top to bottom. Now let us consider a car with 1 psi less pressure at the top than the bottom, with a net frontal area of 12,240 square inch. 12,240 pounds of air pressure will try to lift the car up, and that's how lift is formed. Now to get a desired amount of downforce to keep the car on the track, we tapped into Bernoulli's principle, which simply states that a fast moving fluid will have a lower pressure than a slower moving fluid. Now a wing that is attached at the back of the car, it makes the air to get faster across it at the bottom than the air on the top. Now the air that flows slowly creates the more pressure, whereas the air at the bottom creates the less pressure, and hence pressure differential is formed, which creates the downforce. But how would you make the air to do that? By making the wing an aerofoil shape. Because when the air runs into a curved surface, it will try to follow that surface, and this phenomena is known as the Coanda effect. The Coanda effect is the tendency of a fluid jet to stay attached to a convex surface. The direction we mount the wing determines whether it is going to have positive or negative lift. The air that has to travel faster speeds up, and due to the difference in the speed, the required downforce is created. It creates negative lift, which is none other than downforce. Now a lot of downforce in the rear tire will cause the front tire to lift up, and it will result in understeer. To counter this situation, the F1 cars have wings, front wings, and the normal cars or the sports car have its smaller version known as the splitters. Now a normal car without any splitter or wing, the air tries to flow through it and create the pressure differential, that high pressure at the bottom and the low pressure at the top of the car, and it results the car to understeer and to lift up. Now in the presence of the splitter, the air that pushes the car stacks in front of it and makes the air to get above the car and creates the high pressure above, and that is how the net downforce is created. For a recap, high pressure at the top, low pressure under the car, and hence overall downforce at the front of the car. Now in normal cars, we don't need such complicated stuffs because they are extremely slow. But we do still find wings attached to the back of a car, be it sedan, be it coupe, or be it a hatchback. Now the main function of it is to spoil the net airflow passing through the car and hence avoiding the positive lift. Since it spoils the net airflow, it is known as the spoiler. The motto of the spoiler is to increase the car's high speed stability. Now in the commuter market, efficiency is the name of the game, and the manufacturer quickly realized that the nooks and crannies present in their cars created a lot of turbulence, whereas streamlined cars created no or very less turbulence. Now a less turbulent car gives the engine 25% more efficiency, and hence a more efficient engine will give in a more efficient fuel economy, which is very important. For example, it is an advertisement from 1930 of a car showing the advantage of aerodynamics than a non-aerodynamic one. But what is turbulence and how it is created? For instance, when a car moves, The air that sticks with the surface of the car forms the boundary layer, and the air that flows above it is known as the laminar air. Now, the laminar air tries to place the boundary layer and create a vacuum in between them. Now, some of the particles from the laminar air try to get inside the vacuum, and these small particles form the turbulence. Now, turbulence is something which we don't want because it is extremely unpredictable and creates a lot of unnecessary drag. For instance, the turbulence is like a power cut in the middle of this seminar, something which we don't want, right? Now, the Tesla Model X has a drag coefficient of 0.24, which makes it one of the most aerodynamic and the most efficient electric car in the market right now. Recently, the Mercedes A-Class has owns the record with a drag coefficient of 0.22. Now, most of the manufacturers try to take inspiration from a teardrop because of its shape and it being the most aerodynamic. Because efficient cars will try to attract more audience from the globe, and that is the reason why most of the cars nowadays look basically the same. With electric cars coming and taking over the petrol cars in the near future, range anxiety will be a new thing. And to counter this situation, aerodynamics will be one of the best solutions. Until mankind can develop enough renewable energy and drag will not be a factor anymore, then we might see some white-looking cars hitting the roads. Thankfully, we haven't yet. Thank you.
If anybody has any questions, you can use the chat box to ask them now. If not, I'll be moving on shortly.
Move on, Shoham.
Okay, so since there are no questions, I think Swarnava did an excellent job, which I think you can all agree with. It was really interesting to know about cars. I personally don't know much, so at least I have a better idea to what to look for in a car if I ever decide to buy one, or at least which person I should give a call. But it did put my mind to wonder about all the countless experiments that must be done to exactly find out what is the perfect design or what is it, the phenomena that physicists must have found out, and the designs and the interactions. For the next presentation, our Dripto will actually be showing a really cool experiment that he has actually performed in his home, which he is going to share with us. So without further ado, I would like to call upon Dripto Pal with his presentation, Detective Optics.
Thank you, Shoham. A very good evening again to everyone present here. I am Dripto, and today I will be introducing you to a branch of optics called FLIREN imaging. And this is basically just a fancy technique of photography. And it is used because it allows us to see certain things which are invisible to our naked eye. To give you an idea, let's see what's happening here. This is just a burning ping pong ball at the bottom right here. This is the bright yellow flame in the middle. But if you look at the top or at the sides, it looks like purple or bluish purple smoke is coming out. Obviously, that's not the case. This is actually hot air. Now, air or hot air also is invisible, right? But as you know, hot air is less dense than the cooler air surrounding it. And it is this difference in density that is being taken advantage of by this technique to create an image out of something that is invisible. Now, the physics behind it is actually surprisingly simple, and we will see how simple it is a few moments later. But what's even more surprising are actually the applications and how important some of the applications can be. Because intuitively, this doesn't sound like it could be that useful. So I'll just show you one application right now. This is cooking gas leaking from a pipe, as it suggests in the heading. And this is the pipe at the bottom. Now this pipe or tube is the pipe that connects your gas cylinder to your stove. So the highly flammable LPG is traveling through this pipe before it reaches your stove. So obviously an important part of the system, right? Now think of yourself as a manufacturer, and let's say this is the testing phase, right? And you can smell the gas, which is bad, because if you can smell the gas, that means there's a leak. But the smell doesn't tell you where the leak has occurred. For that, you need to know where the hole is, and precisely you need to see where the gas is spraying out of. You need to be able to see this spray. Now LPG is also invisible, but because it's a different gas, it has a different density than the air around it. And again, that's why we can use FLIREN imaging to detect leaks of LPG from pipes, and also to detect leaks from almost any gas from almost any container. For example, the gas cylinder itself could be tested for leaks using FLIREN imaging. So this gives you an idea of how important this is and how it is used to test things that we use in our daily lives. One of them nowadays being the COVID mask. Now you are wearing this for several hours when you are outside, and maybe you are wondering whether this even works, because sometimes it can be uncomfortable. Now you can use FLIREN imaging to show that it definitely does work. As you can see, this is the guy sneezing without the mask, and on the right he is sneezing with the mask, and the mask is drastically reducing the spread of the sneeze, and hence reducing the spread of the disease. Now this is what I actually wanted to talk about, this one. I kind of sped through everything in the beginning because this is what I'm most excited about. You see, study of shock waves is the most important application and most impressive application of FLIREN imaging. Now you obviously know what a shock wave is, I'm assuming. Like you must have seen in a movie where a huge explosion occurs and the shock wave from the explosion destroys all the windows of the nearby homes, right? You must have seen that. Another way of creating a shock wave, other than explosions, is whenever something goes supersonic, which means something moves faster than the speed of sound. One of them being a supersonic aircraft, right? Now let me just explain what a shock wave is very briefly. So this dark line that you see here, that's the outer edge of the shock wave, and this is nothing but a dense region of air. So the air over here is way denser than the air over here or over here. So that's what a shock wave is. It's a dense layer of air molecules. And because this region is denser, you can say that this region has a different density from the air surrounding it, and that's why we can use FLIREN imaging to image a shock wave. Now, suppose you are an engineer in the military and you are manufacturing supersonic aircrafts like this one in the picture. What you actually need to know to manufacture any aircraft for that matter is how the air is interacting with the shape of the plane, which you can do in your lab. You can do aerodynamic tests in your lab. The only problem is you cannot replicate a shock wave around a life-sized model of an airplane inside a lab. That only happens when the plane is actually flying. So far, we don't have the technology to replicate or simulate a shock wave inside a lab around a life-sized airplane. So you can only see a shock wave or create a shock wave when the plane is actually flying, right? But you need to see how the shock wave is behaving with the shape of the plane. Because if you want to know how the air acts or behaves with the shape of the plane, you need to see how the shock wave is actually behaving, because most of the time in a supersonic aircraft, which is moving faster than the speed of sound, the air is nothing but a huge shock wave. So if you are an engineer, what you do is you use FLIREN imaging and you focus on these bright spots right here. See around my red laser pointer. So this bright spot, these lines coming from the top of the wing. What this tells you is how the shock wave is interacting with this curve at the front of the plane, or the shape of the wing, or how it's interacting with this L-shaped air intake, etc., etc. And that tells you where improvements need to be made to make this plane faster. Because you may know the top speed of the plane and how fast the plane is moving, but you also need to know how to make it faster. And that's where FLIREN imaging comes in. But what about an object which doesn't have a cockpit and you have no way of knowing how fast it's moving just by looking at it, right? One of them being a bullet. Why am I talking about a bullet? Because a gun is only as effective as the bullet. So if you are working for the army, suppose, and you are the person who manufactures the ammunitions, you need to make the bullet as aerodynamically sound as possible, which means the bullet needs to cut through the air as efficiently as possible for the bullet to be effective. One of the ways of knowing whether the bullet is effective or not is to know how fast it is moving. But as I said, the bullet doesn't have a cockpit, which tells the pilot how fast it is moving. So how do you do that? You focus on the this outer edge of the shockwave at the front, which I have highlighted with some red lines, right? Now this V-shaped red line or lines is creating an angle at the front right here, this big angle. You take half of that angle. So this was the entire angle. I took half of it. That's called the Mach angle. And there is a bunch of complicated mathematics, and you can use this Mach angle to find the speed of the bullet. We are going to ignore the mathematics. The importance is that we use this angle to find the speed of the bullet. Now think about what I just said. This angle is a visual piece of data, right? Now the shock wave is invisible. So you need to measure a visual piece of data from something that is invisible. So I think that gives you an idea of how impactful this technique of Schlieren imaging is in the field of shock waves or the study of shock waves. So from preventing gas leaks in your kitchen to testing your COVID masks to improving the aerodynamics of your airplane, I think we can safely say that Schlieren imaging is pretty useful, right? So now that we have learned its applications, now this is the simple part, the physics behind it, the theory behind this, how this works. And the way I'm going to do that is by showing you how you can do a Schlieren imaging experiment at home by yourself, because that's how simple the physics behind it is. So all you need is a light source, ideally a point source of light. I'll show you how to make that later. A camera and a blade or a knife, anything with a sharp edge will work. And a concave mirror. Now this is not a plain mirror that you find in your dressing table. This is a concave mirror, which means it's bent inwards. So this side is the front of the mirror and that is the back of the mirror. So if you're standing here on this side, you will be able to see your face. Now this is what the basic setup should look like. The light should be kept close to the blade and the camera should be kept behind the blade. Now the light is emitting light, which is hitting, the light source is emitting light, which is hitting all over the mirror. Now I have just taken the rays which are hitting the edge because that's all we need to understand what's happening, but the light is actually hitting all over the mirror. So keep that in mind. Now, after the light reflects back from the mirror, it will converge right on the edge of the blade. What does that mean? So this is actually my smartphone that I've covered with aluminum foil, and I've made a small hole right where the torch is to create a point source of light. You can do this with a big torch also. Just cover the face with aluminum foil and make a small hole at the center. That will make it a point source of light. Now this right here is a blade. I don't know if you can see it. That's the edge of the blade. And that second bright spot right here is where the light is converging. You can't see the mirror. The light is actually coming from here, hitting a mirror and then bouncing back and converging here. Now, when the light converges, it creates a small circle. And it should be such that half of that circle is hitting the edge of the blade. So half of that circle is getting blocked by the blade and the other half enters the camera behind it. So only half of the light is getting blocked by the blade and the other half enters the camera behind it. That's what I mean when I say converging on the edge of the blade. So this is what the basic setup should look like before you keep something in front of the mirror. Now, for example, I kept something in front of the mirror that generates heat and as a result generates hot air around it. For example, the burning ping pong ball that we saw in the first picture. Ideally, I would say use a candle because it's just way more convenient. So what happens is I've just taken a small section of hot air because that's all we need. Now, if you look here, these rays are completely unaffected. Their path are unaffected because they are not passing through this region, right? But I said before that the light is actually hitting all over the mirror. So now let me consider two rays which are actually passing through this region. If you look right here and right here, so here and here, the light is actually bending. This is because of refraction. So whenever light enters a region of a different density, it will bend. This is called refraction. Now again, when it will reflect back from the mirror, here and here, it will again refract because it's again entering a region of a different density, right? So let me just get rid of the other rays. Yeah. Now, because of this, we will actually get an image like so. So this circle that you see here, this big gray circle, this is actually the mirror. So this light source is illuminating the entire mirror, and this is what it looks like. And that is the candle at the bottom, and this is the column of hot air. Let us rewind a little bit. I mentioned that when it converges on the blade, half of it gets blocked by the edge, half of it gets blocked by the blade, like on the left side of this circle, and the other half will enter the camera behind the blade. So if there was a camera kept behind this blade, the right side of this yellow circle would enter the camera, right? This is when there's nothing in between. Now, suppose you have put a candle and then there's a column of hot air. If you look at the right side of this column of hot air, this is way brighter than the background. By the way, because only 50% of the light is making it into the camera in the basic setup and 50% is getting blocked, that is why the background is only partly illuminated. Like if you look at the background, this region, you can say it is 50% bright because only 50% of the light is entering the camera. Now, if you look at the right side of this column of hot air, this looks very bright, brighter than the background. This is because of all this refraction and bending, the path of the light ray will change. So some of the light rays in this region, which were supposed to get blocked by the blade, their path changed towards the right, like so, and now they are entering the camera. So because of all this bending and changing of path, more than 50% of the light from this region is entering the camera, making this region more than 50% bright, hence brighter than the background. Similarly, as you can guess, on the left side, because of all the bending, some rays of light which were supposed to enter the camera, their path got shifted towards the left and now they are getting blocked by the blade. So less than 50% of the light is entering the camera, making the left side of the column of hot air less than 50% bright, hence less bright than the background or darker than the background. So just to recap, whenever you keep something of another density, for example, a column of hot air, due to all the refraction from some region, more than 50% of the light will enter the camera, and from other regions, less than 50% of the light will enter the camera, making those regions brighter and darker than the background, hence giving us a contrast, hence giving us an image of something that is invisible, right? By the way, that is not always the case. That kind of depends on how your camera is looking at the mirror. Like for example, if you look at the left image right here, that's the column of hot air, and you are seeing dark spots, but the bright spots are kind of the same brightness of the background. That can happen. Basically, all we need is a contrast to make out the hot air. And the reason why this picture on the left looks so nice is because they're using a huge mirror, which is very smooth, and it has a big focal length. Focal length is a feature of a mirror. If you buy a mirror from Amazon, if you want to do it, you can get it for about 200 rupees. I'm just mentioning in case you are curious enough to do this experiment on your own, because that's the whole point of this seminar, right? So try to get one with a big focal length, ideally 100 centimeter for a precise experiment. So this guy has taken such a mirror, and the setup is very precise, which is why the picture is so crisp. Now on the right side here, this is what I did about 2 years ago when I first learned about FLIRN imaging, and the quality of the mirror is less than satisfying. As you see, the focal length is about 20 centimeter, which is about 1/5 of the optimum focal length you need. So definitely not optimum equipment that I'm working with here. And I didn't even bother to set it up correctly because only half of the mirror is illuminated. And yet I'm not ashamed to show this picture beside this one, because see right here, that's a column of hot air. The flame of the candle is out of the frame, but that's the column of hot air rising from the candle, and we can still see it without proper equipment. And I actually had to do some improvisation, which I don't have time to get into. But so that's why I'm pretty proud of this picture. I'm looking at something that I wasn't supposed to look at. I've taken a picture of something that was supposed to be invisible. And that is my whole point of detective optics. Some interesting things in physics are not really that confusing. They are very simple, and they are also really cool. So you can try this at home. I hope you do. So I hope you learned something new. Thank you.
Shreyoshi Bagui asks, You are using a white light consisting of several colors. Why is the resultant image of the experiment in black and white?
That's a good question. The thing is, the white light, yes, it consists all the colors of all of the rainbow, but we are actually not using a filter. All we are using is a blade. So we are doing is we are changing the brightness. We are either receiving more light in some regions and less light in other regions, right? Now that's what we are doing. We are actually just looking at a contrast in the image. So we are actually looking at the best way to put it in terms of physics is we are looking at the density differential, but that's not really a nice way to put it in a seminar. So the easy way to think about this is we are just looking at the difference in brightness in the picture. We can get a colored image, however, if we use a filter instead of a blade. That is also possible.
Okay, thank you, Dripto. I don't see any more questions. It was a really interesting experiment to know about, and honestly, something I have never come across before. So thank you for picking such an unique topic. As an photography enthusiast, it's really cool to know about something about the physics behind some of the photographic techniques, that it is not just light entering film. And speaking of light, light is actually one of the biggest areas of contingency in physics. Physicists have argued over centuries about its nature and what are its properties for real. It has a deep history, and you can almost track the progress of physics in the last few years by just studying the development in the theory of light. Now, to take you through a part of this journey, I would like to call upon our next group, Light Matters.
Light, one of the many wonders of nature, a fuming curiosity to scientists and sages. From dawn to dusk, sunrise to rainbows, there are many curious questions about light. Sunlight, fire, fireflies are some natural sources of light. The computer screen you were looking at, or the commonly used flashlights, are some artificial sources of light. Light, its nature, phenomena, and various scientific advancements brought about by it have been a topic of debate to the scientists and sages. And why was it difficult for them to understand its nature is our today's topic of discussion. Our today's topic, the wave-particle duality, expresses the inability of classical physics to fully describe the quantum-scale objects and various other phenomena, such as relativity. The nature of light, that whether it shows wave nature or particle nature, has been an age-long debate among the scientists, and today we are going to discuss over that more elaborately. Sir Isaac Newton came up with the corpuscular theory of light, which states that light consists of a stream of particles. He came up with this theory because he had a firm belief that only particles could describe straight-line motion. His theory could prove the laws of reflection, refraction, but was unable to give any proper explanation for the phenomena of diffraction. Christian Huygens came up with the wave theory of light, and he could prove the laws of reflection, refraction, also demonstrated phenomena of diffraction, and also demonstrated that how waves might interfere to form a wavefront propagating in a straight line. In 1801, Thomas Young performed an experiment in which he passed a set of beams through two slits and produced interference pattern on the screen, and thus he showed the wave nature of light. The first picture on the screen, as you can see, shows the phenomena of interference, that is superposition of waves. The second one shows the formation of a very distinct bright and dark fringe patterns on the screen if light shows wave nature. On the other hand, we see that such distinct fringe patterns are not formed on the screen in case light shows particle nature. Here are some real-life examples of interference. The first we can see is the superposition of water waves. The second one is an outcome of the Young double-slit experiment. The third one is the interference pattern formed on thin polished surface of CD, and the fourth one, interference formed on thin film of soap bubbles. James Clerk Maxwell, while studying electricity and magnetism, came up with 4 equations which describe the electromagnetic waves. He measured the speed of electromagnetic waves and found it to be almost equal to the then measured speed of light, and thus he proved that light was actually an electromagnetic wave. The picture alongside shows that both electricity and magnetism show wave nature. Later on, his theoretical explanation was proved by an experiment conducted by Hertz, in which he set two oppositely charged metal plates at a certain distance apart. Electrical connections were made via inducting coils, and a high voltage was set between the plates. Due to the passage of a uniform electric field, the air in between the metal plates got ionized. Electric sparks were produced, and the electromagnetic radiations thus produced were observed via the receiver. Max Planck gave the spectral density of electromagnetic radiations given by a black body in a thermal equilibrium at a particular temperature. And later on, Albert Einstein used Planck's model to give a theoretical explanation of the photoelectric effect experiment, in which he stated that light, when falls on metal plates, that is a collection of atoms, then those atoms give off electrons. Only certain frequencies of incident light could give off electrons. Higher the frequency of the incident light, higher was the kinetic energy of the electrons ejected. Later on, his theoretical explanation on photoelectric effect was confirmed by another experiment, the famously known Compton scattering effect, in which both electron and photon collided elastically and both energy and momentum remained conserved. Thus, both photoelectric effect and Compton scattering effect proved the particle theory of light. The further story of light will be conveyed to you by my teammate Rijik.
After Einstein concluded that light behaves like particles, physicists were kind of thrown in for a loop. And that is when a French guy named Louis de Broglie hypothesized that maybe, just like light, matter itself could also exhibit wave-like properties. And to top it off, he even gave an equation relating the wavelength to the momentum. As surprising as this sounds, he was later proven to be right. The reconciliation of the particle nature with the wave character of light has brought about the development of modern quantum theory. And perhaps the best known consequence of wave-particle duality is the very famous Heisenberg's uncertainty principle. What it tells us is that quantum objects don't have definite values for certain pairs of properties. For example, position and momentum. The fascinating thing about the uncertainty principle is that this is not a measurement problem. The uncertainty principle is inherent in the properties of all wave-like systems, and it simply arises in quantum due to the matter-wave nature of quantum objects. To illustrate this, let us say we know the exact momentum of a particle. We can then represent this as this infinitely long sine wave, and the area and the probability of finding the particle at a point can also be obtained from this curve by calculating the area under it. But as this curve is of infinite extent, so the area is going to be same everywhere. So it is impossible for us to tell where the particle is. But we can do better. To get a better understanding of the particle's position, we can use this property that waves have, which is if we add a bunch of them together, they combine to produce a new wave. Now in this case, we can see that the particle is much more localized. So we have way better understanding of where the particle is. But remember, to do this, we had to add a lot of different wavelengths together. And from de Broglie's relation, we know that the wavelength and the momentum are interrelated, which means in trying to gain information about the particle's position, we automatically lost information about the particle's momentum. Now, ever since the development of quantum mechanics, the way we view the universe has changed drastically. To give you a glimpse of how it has even crept into and revolutionized other areas of physics, I would like to talk about a very well-known and fundamental principle in all of optics called the principle of least time given by Fermat in 1662. Simply put, it tells us that light always seems to minimize the time it takes to travel between 2 points. Now, although the concept behind this is pretty simple, this idea has some remarkable implications because using this we can arrive at the laws of deflection, refraction, and even the principle of reversibility. In fact, this principle serves as the link between geometrical and wave optics. But keeping all its uses and importance aside, if we stop to think about this for a bit, what we will see is that this is a very weird philosophical principle about the way nature works. Because what we are essentially saying is that we set up some kind of a situation where light needs to go from one point to another. And then somehow, some way, light decides by itself that which path is the shortest time or the more extreme and accordingly chooses its path. But we can ask this question, right, that how does it find out? There is really no way for it to know. And this is why probably this principle eluded explanation for nearly 400 years until the result was finally understood in the latter half of the 20th century using the probabilistic theory of quantum mechanics. Now, to see how this works, let us consider this example of diffraction. Now, what we must understand is that since this is quantum, light can no longer be treated as a wave, but instead now consists of individual photons. And everything we do from here on out will involve calculating probabilities. So let's just ask ourselves a question. What is the probability a photon leaving A reaches the point B? Well, luckily for us, there is actually a rule in place for calculating this probability. We begin by considering a possible path from A to B. Then we calculate the time taken to travel that possible path. The next step is to construct this complex vector which is proportional to e to the power I theta. Now, if this is bugging you, you can think of this as an arrow where this angle theta is an angle made with the x-axis. Now, this angle theta is a function of time. So over time, this arrow spins around, and depending on which path we take, it ends up pointing in different directions. Repeating this same process for every possible path, we end up with a collection of arrows. The next and final step is to add all these arrows together, just like we would at regular vectors, and then quantum says that the probability is proportional to the square of the length of the final arrow. But at this point, you may be wondering that how does doing any of this help us in interpreting Fermat's principle? Well, to make that connection clear, let's just line up all these arrows under this graph, which represents the time function. What we immediately observe is that the arrows just under the minimum of this curve are all roughly pointing in the same direction, while arrows far away from the minimum are randomly oriented. But actually, this isn't all that surprising because the gradient far away from the minimum is much steeper than it is close to it. What this means is that the paths that mostly contribute to the total probability are the paths punched up with the least time paths, while arrows far away from the minimum, being randomly oriented, tend to loop around and cancel each other out. That's why light always seems to act lazy and takes the path which requires the least amount of time, because probabilistically speaking, it has a greater chance of doing so. Now, to prove to you that everything I did up until now wasn't just some weird match trick and that each of these paths are important and that they contribute to the total probability, I would like to do a final demonstration. So say we want to make a system which somehow somewhere focuses light. Well, for that, we want all of these paths to arrive at a point simultaneously. But as you can probably guess, this isn't possible because the straight line path is obviously going to be much faster than the others. But actually, there is a pretty neat way of getting past this. Since we know that a material like glass slows light down, we can just insert some glass in the way to compensate for the travel time. Since every path is different, every path calls for a different adjustment. And when we do that, we end up with a structure which looks something like this. Something I guess we are all familiar with. That's just a convex lens. And speaking from a quantum mechanical perspective, that's basically how lenses work. It compensates for the travel time in a way that more paths, instead of just cancelling each other out, contribute to the total probability. That's why this shape seems to focus light. So you can see the power of quantum in that it can even be used to explain the workings of everyday objects like lenses. Next, Srijita will further elaborate on why it is important to incorporate quantum mechanical ideas in the models that we develop in our quest to understand the universe.
After all these discussions, the one question that comes to our mind is that why do we need a theory like quantum mechanics? Because it describes so many features of our universe where classical physics failed to give any proper explanation. For example, the small-scale discrete particles and the interactions between them, or the subatomic particles, or even some of the bizarre phenomena like theoretical cats, which can be both dead or alive at the same time, or indecisive photons that can go anyways two ways at once, and also the particles kilometers apart that can neither communicate instantly. It is necessary to know about such a theory because of all the technological advancements that it brings to our modern life. From our basic necessities like toasters, personal computers, Blu-ray players, transistors, nothing would have been possible without quantum mechanics. Even the sun, which is an integral part for the survival of living beings, would not function without a phenomena called quantum tunneling, a phenomena so mind-blowingly weird that particles could penetrate through waves. And central to all these ideas lies the principle that everything around us is made up of elementary particles which could be modeled as waves. uh, what began as an attempt to describe the nature of light and describe the nature of heat in solids gradually led us into one of the most perplexing yet elegant theory mankind has ever come up with. Thank you.
Okay, so I have a question. Light is massless. If we put m as 0, we get infinite wavelength. But light has finite wavelength. What is wrong here?
So, this is a good question. Uh, the idea of momentum, we can say that the idea of momentum in case of light is different than our normal intuition. So, we can say that momentum is not always m into v for a photon which has no rest mass. The equation is p is equal to e by c, where c is the speed of light, and thus we can say that there is nothing wrong here, but we can only say that the idea of momentum in case of light is different than our normal intuition. That is the idea that we use here.
I would recommend Cristiano Ronaldo to stick to Euros right now. Don't think about physics. So moving on to the next question from Yosha Jaria. Does light always travel in a straight path, or does it travel in curved paths too?
The thing is that about light, since light has a very small wavelength, so if we want it to display wave-like properties, which is supposedly described as a curved path, we need an object which has a size comparable to the wavelength of light. So in general, for objects like lenses, which are pretty large, say in centimeters, then light will move in straight lines. But if you can perform the double slit experiment, say, where the slit width is very small and comparable to the wavelength of light, then light will diffract and it will show wave-like properties. So then light will not show straight line motion anymore.
Okay, thank you, Richik and Srijita, for that really informed analysis on the nature of light. I know it sounds crazy to think about how light can exist as both an wave and a particle at the same time, but hey, that's quantum mechanics for you. If anything is clear from their discussion, I think it is that light is a very complex thing, and it is seriously one of the most vast fields of study in physics. Its theories have such large implications in the entire physical world that we are still studying light to this day. An interesting thing about light is that it is actually the fastest thing in the universe. Nothing goes faster than that in the universe. But there is something that even light cannot escape. I think you know what I am talking about. It is a thing of mystery and enigma in our universe, stuck in darkness of the world. I would like to call upon our next presenter, Hashibul Haq, to explain this thing that exists in our mind. I think we all know it, but we don't really understand it. So let me just give it up to him for his presentation, The Black Beauty.
Hello everyone, I am Hasibul Haq from Physics Department, the Heritage College. Let us have a talk about Mr. Black hole. So once upon a time there was an idea. In 1783, a British astronomer named John Mitchell wondered what would happen if gravity of a star becomes so strong that nothing can escape from it. Nothing means light itself cannot escape from it. So his so-called dark star question was lost until a century later, Carl Schwarzschild, a German physicist, solved an exact solution of Einstein's theory of relativity and found a similar star. At present, we know these stars as black holes. Carl Schwarzschild also found that for every object, there exists a radius known as Schwarzschild radius, beyond which, if the object is compressed, the object will become a black hole. Now, what is black hole? Black holes are the most powerful and extreme things in the universe. They are wildly weird and complicated. A black hole is a region in space-time where gravity is so strong that not particles, not even electromagnetic magnetic radiation such as light can escape from it. So let's first understand about space and time. Space and time, like a grand stage where plays of the universe unfolds, but space isn't a fixed stage and time doesn't tick the same for everyone everywhere. In short, they are relative. Put some stars and planets on the stage, it will sag underneath them, and this little misshapen warps and dips gives us gravity. Black holes do not just bend the stage, but they are like trapdoors, or literally holes in the stage. Black holes are places with so much mass that universe itself formed a no-go zone where the rules of the physics changes. Now an obvious question is, okay, light cannot escape from it, then how can we observe a black hole? We can still observe a black hole due to its effects on matter. Things can orbit a black hole as like matters can orbit a planet or stars. So many black holes have disks of matter orbiting outside the event horizon. This matter can become incredibly hot as close orbits can speed this matter up to half the speed of light, and tiny amount of friction and collision between these particles can heat these particles to 1 billion degrees, making the space around these black holes are ironically bright. And if there are stars that are orbiting a black hole, we can use their orbit to determine the mass and location of the black hole. Now another question is, what will happen if we get too close to a black hole? First of all, you would see the strangest funhouse mirror in the universe. Matter isn't the only thing that orbiting a black hole. Gravity is so strong that near them that light can orbit it too. If you hover just outside the event horizon at the photosphere, in any direction you would see yourself. Straight ahead would be the back of your own head, as light from your own back can travel around the black hole and come to your eyes. Now another thing happen is passage of time alters. We call it time dilation in physics. Gravity can alter the passage of time itself. The stronger the gravity, the slower time passes. So while you watch the universe above you speed up, those far away will watch you in slow motion. But getting close to a black hole can be incredibly dangerous. A painful death by spaghettification awaits you. The immense gravity of the black hole would compress you horizontally and stretch you vertically like a noodles, which is why scientists call this phenomena spaghettification. So your body will be squeezed thinner until you have been reduced to a thin stream of hot plasma. Now let's talk about properties and structure of black hole. Most of every black hole have event horizon and singularity, and many of them have accretion disks and relativistic jets, depending on whether matter orbiting the black hole or not. And for rotating black holes, there are ergosphere and angularity. We'll talk about them. Now first let's talk about event horizon. Event horizon is the boundary of defining the space of around a black hole, from which nothing can escape, not even light, or it is like a point of no return. So it is not a physical surface, but a sphere surrounding a black hole that marks where the escape velocity is equals to the speed of light. Another interesting fact is event horizon is called the event horizon because events beyond this horizon cannot reach the outside observer, making it impossible to determine whether such an event occurred or not. Now let's talk about singularity. Space-time singularity, or simply singularity, is a point where the density and gravitational field is infinite. The singularity has no surface or size, something like a divide by zero error in the universe. Everything you ever heard about black holes is about the black holes that are not rotating because the math are easier. But since black holes were born from dying stars that were rotating extremely quickly in the last moments, as far as we know, every black hole in the universe would be rotating right now, and at incredible speeds too, up to 90% speed of light. This means in reality, black holes are even more screwed up than they usually get credit for. So the gravitational singularity or singularity of a rotating black hole is known as singularity or ring singularity. Shaped like a ring, and it have a thickness of 0 with no surface area. Another interesting region is around around the outer event horizon of rotating black holes is called ergosphere. Uh, Inside ergosphere, nothing makes sense. It is possible to enter it and then leave it again. The singularity makes you dance whether you want or not. It is like wave pool. You need to move faster than the speed of light just to stand still, which is impossible. Like everything, we have found a way to harvest energy of black holes. We can steal as much energy from it as every star in the Milky Way emits in a billion years combined. The easiest way to steal this energy is early enough to drop something into the black hole, and it will give us energy. We know that the singularity forces energy on us when we enter the ergosphere. So there is a process named Penrose process, which means that if we send a rocket into the ergosphere and make a trade that we will give some of our mass energy and it will give some of its rotational energy. And the boost from this rotational energy of the black hole is so big that you leave the ergosphere with much more energy than you entered it. Maybe in future our descendants will live near a black hole, or they will make bombs with black hole. Who knows? There will be humans too. Everything that has born has to die. So let's talk about the death of black hole. To know about death of black hole, first we need to know about Hawking radiation, and to know Hawking radiation, we have to look at empty spaces. So according to quantum mechanics, that empty spaces is not really empty, but filled with virtual particles popping into existence, annihilating each other. When this happens right on the edge of the black hole, one of the virtual particles will be drawn into the black hole and other will escape from and become a real particle. This member that doesn't fall into the black hole then emitted from the black hole, known as the Hawking radiation. So basically the black holes is losing energy, but this happens incredibly slow at first and gets faster as the black hole becomes smaller. When it arrives at the mass of a large asteroid, it's radiating at room temperature. When it has a mass of a mountain, it radiates about the heat of our sun. And in the last second of its life, the black hole radiates away with the energy of billions of nuclear bombs in a huge explosion. But the process is incredibly slow. The biggest black hole we know might take up a Gogol year, that is 10 to the power 100 years to evaporate. This is so long that when the last black hole radiates away, nobody will be there to witness it. Now I would like to conclude with a small statement that the universe will end with a big freeze or a big crunch. But black holes will be there lonely in the sky, nobody to witness their existence, not their destruction. Or maybe our descendant will be there, living near a black hole in a dying universe. Thank you for being an awesome audience. Thank you.
Bidisha Chatterjee asks, I have a silly question here. Do you think it will be possible to create something like black holes in lab one day?
Yes, theoretically possible. Stephen Hawking theorized that there are black holes that are that have a size of 10 to the minus 36, way more smaller than the atoms itself. So he theorized that if we collide two particles at a really fast, then this can provide the energy to form those particles a black hole. I'm not sure. I mean, I am not confident in that, but I am. I think you got the answer.
Next, Ankur Haldar asks, what will happen if our sun turns into a black hole?
First of all, that our sun cannot be turned into a black hole because its size is too small to become a black hole. And if hypothetically our sun becomes a black hole, our orbits of our planets of our solar system will not be affected, because it has the same gravitational pull as the sun. It will have that same, but we will be dead because we will have no energy for living. Another thing is that I created a Google Doc links. I'm giving it to the chat box for further reading. Please go through it. Thank you. Thank you.
Okay, thank you, Hashibul. That was a really ballsy topic to pick up. And black hole is something that is filled with mystery, and we don't really understand it fully yet, but there are a lot of research that is going on in it. And I really commend you for trying to discuss it and explain us as much as you could. An interesting thing about black hole, or an hypothesis, I must say, is that it can facilitate time travel at some point. I'm not gonna explain it much, but think of it like an cosmic shortcut in our world. Like you can go from a point A in point B in our space-time continuum very quickly. So in which way you can actually time travel. Now just think of what will happen if somehow we get hold of this technology. Let's, for the case of discussion, let's just imagine a physics student before the night of his exam. He's obviously frustrated by the amount of syllabus he has to cover and the amount of research that has gone into which has led to this syllabus. So he decides to take a drastic step. He goes back in time and decides to kill Sir Isaac Newton so that the following research that has happened so far never exists, and he returns to a reality with a much shorter syllabus so that he can quickly get his degree. But is it that simple? Does one action in the past certainly affect a future in such drastic ways like the butterfly effect suggests? Well, you see, there is a logical fallacy here. It says that if the syllabus never existed in the first place, why would you have gone back to reduce it? And to discuss on this logical fallacy or paradox, I'd like to call upon our next group because it is actually a very deep problem in our physical world. So let us give it up for our next group, The Boy Who Lived.
Hello, everyone. So, from our childhood, we all have looked up to the sky and thought about how big this universe is. What lies outside? Is there another? We owe these thoughts to the vastness and the subtle ambiguity that nature beholds. For all that we did was just to look up at the sky, and it rained down fragments of marvelous thoughts. And those thoughts would have been meaningless and shapeless without the key ingredient we often overlook while we grow: curiosity. It is this curiosity that leads to the greatest minds unfolding the truths, or rather, minds unfolding the greatest truths. It is from our childhood days only that we did fall in love with this very smell of curiosity towards nature, which got us inclined towards physics, way before we learned the word physics. And it is the sky only that we do look up to when we think. And so, there's a thought, or shall I say, a question. It is the story of the boy who erased the reason of his existence. It is the story of the boy who lived. The series of events that has already manifested in reality can't be changed. The very weird postulation of going back in time to actually change what has happened has been existing for a very long time. Not to discuss in binary whether it is possible or not, we would like to keep our answers for the audience to scratch their heads on.
Have you ever thought that if you went back in time and maybe changed something, that's a reason for your regret today? Well, if that has been true, then you might have also thought that your present might change since your past has changed. And the things that led up to your present might also change and make you currently a different person from a different origin. To exaggerate this feeling, I might or rather must pose the concept of one killing their grandfather in his childhood days so that there's no possibility of him being in existence. This is the so-called grandfather's paradox. The cycle goes on like this. Suppose on a day you decide that you're going to kill your grandfather. Not now, but back in time when it became, not now, but back in time when he was a little boy. Now, then it becomes a question of your appearance too in the universe, and therefore your grandfather doesn't die. Now, since your grandfather lives, you live, and then again you decide to kill him, and this loop goes on and on. Now, what is this grandfather's paradox? Grandfather's paradox is a potential logical problem that arises in the path of time travel. It says that if you kill your grandfather before the existence of your mother and your father, then the traveler's existence will become questionable. Now, you must wonder that why is this a paradox? I am killing my grandfather, I am traveling back in time and killing my grandfather, and obviously my existence will simply obviate, but it is not that simple. To answer this question, we must look at the basic or the fundamental rule of time travel, which says that whatever you do to change your past, it is not going to affect your present in any way. That is, your present will always remain unaltered regardless of what your past events are. And thus, grandfather's paradox, according to many scientists, is an obstruction in the concept of traveling to your past. Well, to this paradox, there's also a solution proved by two scientists from Australia. Let's say that even if you do go back in time, taking time travel into consideration and change some events according to your liking, you would feel, wow, now I have made the amendments at the correct time coordinate, and so by my calculation, I will be successful by now. But only to return to the fact that what? Everything's still the same. How? I changed my past and consequently my present should change. And the only thing you're left with is, it is what it is. The scientists have provided the proofs that refer to the fact that however you change your past, your present will remain the same. By the fact that the events that you had altered would change accordingly to bring the same present that you had been in when you traveled back in time, by means of what we commonly know as the butterfly effect. Well, let's imagine when we do go back in time and change the events, we do enter a different universe which had different branches of probabilities. This in order brings forth the idea of multiverse, which seems to be a potential solution to this paradox.
If you are a fan of science fiction or fantasy, then chances are that at some point you might have read a book or even seen a movie that talks about the multiverse theory. So, what is this multiverse theory? Well, the multiverse theory states that there may be multiple or even infinite number of universes, including the one that we consistently experience, that together comprises everything that exists. And by everything, I mean the entirety of space, time, matter, energy, as well as the physical laws and the constants describing them. In this context, multiple universes can be referred to as parallel universes as they exist alongside our own. So, who came up with this term multiverse? Well, the term multiverse was first coined in 1895 by the American philosopher and psychologist William James. Though the existence of a multiverse is a debatable topic, however, the scientific basis of it arose from the study of cosmological forces like the black holes and the problems arising out of the Big Bang. Theories like cosmic inflation supports the existence of a multiverse, stating that countless universes emerge from the same primordial vacuum and that the universe as we know it is just what is observable to us. Now, you might think that how did we come up with the idea of a multiverse? Well, the idea of a multiverse didn't just get thrust onto the society by imaginative sci-fi writers. It was actually born out of other premises like the string theory and quantum mechanics. Anyways, the existence of a multiverse opens up many interesting possibilities, as many authors have envisioned over the years that if there are infinite universes, then it might be possible that in some there exist doppelgangers of ourselves. But even if these alternate versions of us do exist, they might be experiencing a completely different physical reality, as the laws of nature aren't necessarily the same for every universe. Now a question might arise that how can we prove that a multiverse does exist? Well, according to scientists, if our universe collided with another, then it would offer some evidence, and some theorists have stated that colliding universes could leave behind cold spots or hot spots
on the cosmic microwave background, or the CMB, which can be referred to as the afterglow of the Big Bang? And if so, then we should be able to detect these curls through advanced sky surveys. Also, gravitational waves or ripples on the fabric of space-time could leave behind some tiny spots on the CMB, which some telescopes are actively searching for today. If researchers succeed in detecting these spots on the CMB as they thought they did in 2014, then it could really boost support for the idea that there's another version of us out there going about their daily life in an alternate universe, and hence supporting the existence of a multiverse.
The boy can live if we understand what superposition is. Superposition is exactly what the name suggests. By this time, we already know that particles have wave nature, and waves superpose each other. In quantum world, an electron doesn't exist at a particular spot, or even its action isn't of one particular wave. Rather, they exist as a superposition of various probabilities. Two or more quantum states can be added and the result will be another valid quantum state and vice versa. A physical example of the wave nature of particles is the interference peaks from electron beams in Young's double-slit experiment. It was Erwin Schrödinger in the 20th century who developed his famous equation to describe the wave nature of particles, which changed the whole idea of modern physics. Now, let's come to the concept. Assume that I have an electron and its wave nature is spread across a small area. We know that it will appear as a particle at any particular spot when observed. But until observation, its particle form will situate at every possible points in that area. But when observed, its wave nature collapses and it appears as a particle. Anton Zeilinger, with reference to the Young's double-slit experiment, has said that it has been observed that the interference pattern is only observed if and only if the path taken by the electron is unknown. If we place an observer near the screen or even near the slit, then the electron behaves as a particle and its wave nature collapses. This concept gives birth to the concept of multiverse. Let's assume that a particle has 3 points A, B, C where it can appear, and it eventually, when observed, appears at point A. Then we can say that in some entangled universe it has appeared in point B, and in some other it has appeared in point C. We can only imagine how many entangled universes are there which consists of things that didn't occur in our world. The universe is made of billions of trillions of atoms, the same one that forms stars, moons, and possibly multiple universes, and the same ones that ends at the very core of our hearts. So why can't we think that our future, our past, everything behaves just the way our very fundamental beings, that is, atoms, do? There are things beyond our imagination, things that we cannot perceive, things that are too good to be true. Our imagination, our reality, everything comes down to one point, to one truth, that is present. That is all we can and cannot see right now, right here. The boy can live and we still question our reality. We can think that the boy lives because he was meant to be. We kill the grandfather, which is just a representation of playing with time. A ripple in the past can cause tsunamis in the present, but that's all we can think of. The boy can still be going about his day eating a Sunday ice cream in some parallel universe, while his grandfather and as a result him are facing an existential crisis in some other. The result remains same, just that the path taken has to be unknown. The boy lives. The result remains same, the path followed has to be unknown, and the boy lives always.
Things happen in the way they were meant to. In spite of alterations, event collide with each other, almost like they refer to the same probability. It is to our expectations that we change according to the wishes of ours, and it is to our awe that nature is so miraculous. To various discrete views at times, we fail to comprehend the subtle duality hidden in the fabric of cosmos. To this, we also might try to find the whereabouts of possibilities, which is not only highly debatable, but also better left unknown. Coming a long way through the dire course of nature, that we have come this far to actually think there's a different space outside this universe. To actually think there's an end to this endless space. To actually think there might be a different me in a different universe. And to actually think our ideas to be limitless while they all might be limited too. And all along in this journey through the stars, it is often do we question that will that created us.
Our first question comes from Ankur Haldar. How can two different universes have different timelines?
Hypothetically, time also has a particle nature. Time particles are called tachyons, and the superposition of tachyons can create different timeline in different universe.
Okay, the next question is from Pratyay Patro. Does the existence of grandfather paradox prove that the fundamental theories of physics are incomplete?
Well, to properly answer this question, we have to understand what a paradox is. It is basically a self contradictory statement. These kind of logical fallacies can arise in any field, and although how much weird this kind of paradoxes might sound, their existence always point out that there is something incomplete left out, and until that is found, we can never say what we have is correct or incorrect. And to add to this, physics physics is complete on its own, and more of this kind of paradox and more of this kind of paradoxes and exceptions come up. It just like add to that statement, as I said.
Okay, thank you, Utsho, Kotha, Paurobi, and Sharbajita. That was a really beautiful presentation. I think it was David Mitchell who wrote something along the lines of, "We are not on our own. We are bound to each other, our crimes and kindness, each birthing a multitude of futures." Paraphrasing, of course, but I think that sums it up beautifully. And it actually got me wondering about, if there is a multiverse, are there multiple me's out there? Like, what is the doppelganger of me in another alternate reality up to right now? Because if there are alternate realities, I would definitely want to be one where COVID never existed, and we can actually do this seminar in front of you guys, where I can actually see all of you I'm speaking to right now. But alas, we are not. Otherwise, I would also like to be in an alternate reality where I look like Brad Pitt. And that is also not happening. And if it looks like I'm talking just randomly right now, it's because I don't know what the next topic is. I know I'm the MC, but the next group wants to keep it really hush-hush, and they haven't even told me the topic. So I will just know that waste any time and give it up to them. Here's our next group, the Hidden Village of Light.
Almost correct, Shoham. I can understand why you said light, because all we've been discussing about is light. It's the hidden village of sound. Well, a very good evening to everyone present here. I, Shaunak Mukherjee of the Physics Department of the Heritage College, would like to thank each one of you for taking time out of your busy schedule in this difficult phase that we are going through and attending this seminar. As he said, I'm not going to reveal the topic of our discussion right now, but rather I'd like to gradually walk each one of you through a series of observations that helps us to unveil a remarkably interesting topic that we're about to discuss today. And by we, I mean our group named the Hidden Village of Sound, represented by I myself, Akash Ghosh and Madhurima Ghosh. First, I'd like to state one observation and then a fact. The observation being that I believe all of us here are familiar with the scene where a loud source of sound shatters a glass, right? As a kid, I used to think that it is the loudness of the sound that shattered the glass. But is that the case? Can the glass be broken at any level of loudness, or is there a particular level that has to be reached? Now to come to the fact. In the month of April in 1831, a brigade of soldiers marched across the England's Broughton Suspension Bridge. And according to the accounts of the time, the bridge broke apart, throwing dozens of soldiers into the water. The picture you're seeing here is of the rebuilt bridge in 1883. Now, I believe all of us here have seen the Howrah Bridge, right? The mighty structure through which hundreds of cars and buses are passing through every single minute of every single day. The very interesting fact about this bridge is that marching isn't allowed over here either. Well, generally marching isn't allowed on any bridge, but I mentioned Howrah Bridge specifically so that all of us can visualize the thing. Now, of course, the question arises, right? Why does a bridge that can hold hundreds of cars and buses is so easily broken by a few marching men? Of course, it is not related to the weight as the cars and buses outweigh the men. Then it must be related to the marching. These two very distinct cases I mentioned, first, the shattering of glass, and second, not allowing marching on bridges, are very easily explained with the help of phenomena, which is our topic of discussion today, known as resonance. To carry the discussion further, I would like to invite Madhurima Ghosh.
We hear the word resonance used a lot in physics, but let us take a second to ask what is resonance. The word resonance comes from Latin word resonatio and means to resound, means to sound out together with a loud sound. In order to explain the word, we first need to be thorough with the following terms. The first one is period, the amount of time taken by a wave to complete one wave cycle. And the second one is frequency. The number of cycles in 1 second is the frequency of oscillation. And the third one is natural frequency. It is the frequency at which a system tends to oscillate in the absence of any driving or damping force. It is also known as eigenfrequency. Now let us understand what is resonance exactly. The dictionary defines resonance as the state of a system in which an abnormally large vibration is produced in response to an external stimulus, occurring when the frequency of the stimulus is the same or nearly the same as the natural vibration frequency of the system. Physics defines resonance as a phenomena in which an external force or a vibrating system forces another system around it to vibrate with greater amplitude at a specified frequency of operation. Resonance occurs when a material oscillates at a high amplitude at a specific frequency. We call this frequency the resonant frequency of the material. Here we have three identical pendulums that are being acted upon by external forces of different frequencies. And the frequency of the force acting on the middle pendulum is close to the resonant frequency of the pendulum. As a result, the amplitude of vibration of the middle pendulum is very large compared to the other two pendulums, which are not being acted upon by forces of frequency close to the resonating frequency. Now let us come to how resonance was discovered and developed from the mid-17th century. In the mid-17th century, Galileo noted that one man pulling in the right way on a heavy pendulum could drive it into such large motion that it could then readily lift 6 men into the air. In the 18th century, Leonhard Euler solved the differential equation of forced vibrations and concluded that in the motion of a driven oscillatory system, there exist two components at different frequencies, the forced frequency and the natural frequency of the driven system, and also considered the case of when the two frequencies became equal, concluding that the amplitude of the oscillation in that case would increase to a great extent. In 1902, Sommerfeld conducted an experiment where he arranged for a wobbly table to support a heavy machine whose power was continuously increased, which pushed the machine faster and faster, approaching the resonance frequency of the table, and it began to vibrate more violently. Now, I am about to give an explanation to the first observation that was highlighted at the beginning of our discussion of resonance. I will try to make you understand how a glass is broken due to sound waves. But before I give an explanation, I would first want all of you to carefully watch this video by Professor Walter Levin, who I believe is quite popular among physics students and teachers.
I'm sorry to interrupt you, Madhurima, but Suchismita Das, could you please turn off your mic? Thank you. You can resume.
Okay, here as you can see, Professor Walter Levin changes the frequency and loudness of the sound. When the frequency reaches a certain specific value, then the glass breaks. Now the question is, what is the specific value of the frequency? Well, the first thing to consider here is that glass has a natural frequency, a frequency at which the glass will tend to vibrate in the absence of an external force. When frequency of the sound wave becomes equal to the resonating frequency of the glass, then all the atoms of the glass are set in vibration at a very large amplitude, and with increase in loudness of the sound, the vibration of the glass further increases, thus finally breaking it. Thus, we conclude that the loudness alone is not responsible for the breaking of the glass. As long as the frequency of the sound wave is not close to the resonating frequency of the glass, there is no possibility of the glass breaking. Now, one thing that we all wonder while studying something is that why are we studying it? Why solve such difficult equations if the end result is not helpful to us? Now, I would request Akash Ghosh to help us understand the various applications and uses of resonance.
Well, I'm sorry for the interruption. I had a bit of problem in the software actually. So let's continue with our topic. Remember the two questions we asked at the very beginning of our session. The first was regarding the shattering of glass, to which I believe most of us have a concrete answer to right now. Now, coming to the second topic, that is, why soldiers aren't allowed to march on any kind of bridge. But before diving into the topic, I would like all of us to see a video regarding an incident that occurred at the Tacoma Bridge in the year 1940. The Tacoma Narrows Bridge was inaugurated in the year 1940 in Washington, US. But what happened soon after was that when winds of speed 42 miles per hour blew against the bridge, it set the bridge structure into vibrations whose frequency by any chance matched the natural frequency of the bridge, leading to large resonant vibrations as you see right here in the video. And as the wind speed increased, these vibrations too increased in magnitude. And soon the inevitable occurred. Luckily, there weren't any casualties involved with this incident. Well, if winds can set a bridge into such motions that can lead to such destructive effects of resonance, I think we can all have a guess what would occur if we allow soldiers to march on top of a bridge.
Well, if the frequency of footsteps of soldiers match the natural frequency of the bridge, it will set the whole structure into large vibrations, large resonant vibrations, in fact, leading to destruction of the bridge eventually. So it is fascinating, isn't it, that for destroying a large steel structure like the Howrah Bridge, we would not need any expensive machinery. We just need a battalion of infantry and the order for them to march on top of it. Now, I think this might be a common question in everyone's mind. That are human beings so stupid that they ignore these adverse effects of resonance? Well, that is not true. Human beings do come up with solutions to these effects. And one such application, in fact, is used in construction of skyscrapers and high rises. The Taipei 101 once is the tallest building in the world. What very few people know about this massive structure is that it contains a 660-ton pendulum inside it, which acts as a mass damper. And by a mass damper, I mean that it dampens any kinds of vibrations occurring in the steel structure, thus reducing the probability of resonance to occur. In Japan and US, when they construct high-rises and skyscrapers, they build the steel structure in such a way that it evenly distributes the seismic vibrations during earthquakes. And by distributing these vibrations, the probability of resonance is thereby reduced, thus preventing further damage during earthquakes. Now, if we take this phenomenon to an even higher level, we reach the International Space Station, right? The ISS is built of different parts which are called modules, and one such module is the VESTA module, which contains the rocket engine. The astronauts residing there upload parameters which enable these rocket engines to fire, thus changing the height of the orbit. What happened on 14th of January 2009 was that, by mistake, incorrect parameters were uploaded. Well, this led to the misfiring of those very engines. Now, suppose I am driving a car, right? If I accelerate the car and then at the very next instant I slam the brakes, what will occur? Of course, a jerk will be applied on the car. Similarly, due to the misfiring of these rocket engines, a jerk was applied on the ISS as well. And this jerk caused vibrations in the whole structure whose frequency matched the natural frequency, thus leading to large resonant vibrations lasted for 1.2 seconds. This incident put massive structural damage on the ISS and put questions for the longevity of the ISS in the orbit. Well, I think it might have been a bit difficult to visualize these examples till now. Well, no worries. I have alternative easier examples too. You see, as a presenter, I must keep these alternatives in my hand as plan A, plan B, and plan C. Else, I think we would all end up like Manchester City in the Champions League final. Okay, jokes apart, going back to the topic. You see, we all have tuned a radio at least once in our lives. Now, what do we actually do by tuning in the radio? You see, by tuning, we actually change the frequency of the internal components of the radio itself. And the radio stations emit their broadcasts at certain frequencies, which is known nowadays by the names of 92.7 FM, 98.3 FM, and so on. So by altering the frequency, these two frequencies, we try to reach the frequency of the broadcast. And thus, this leads to resonance, and thus we get to hear the sound or the music from the radio stations. Well, for a topic like resonance, it has vast applications in research field. Here are two such researches from recent history. We all know the human nervous system, the human brain, the spinal cord, and the nerves. So what the nervous system actually does is that it passes electrical impulses through the nerves from the brain to different parts of the body, and these impulses contain I should say information from the brain to the different parts. Now, a research paper published in October 2019 showed that it is due to resonance that different impulses arising from different parts of the brain, having different frequencies, coordinate, merge, and pass through different parts of the body, thus giving rise to the human consciousness as we know. Thus, for performing a simple task of hands, feet, and so on, resonance actually plays a major part. Let's come to the topic of cell phones. Sending messages, downloading documents, opening web pages. There are various uses of cell phones. Now, a cell phone is basically a transmitter and a receiver of electromagnetic waves, and these EM waves carry data through them. Cell phones contain sensors, and it is through resonance these EM waves are intercepted and converted to data which you get to see on the screen. And it is a fact that higher the frequency of the EM waves, the faster the data is either received or transmitted. Cell phones work on gigahertz EM waves. In January 2020, a team of physicists discovered a method for detecting terahertz EM waves through the help of magnetic resonance method. Now, what is terahertz? Terahertz is nothing but a higher unit of frequency which equals 1000 gigahertz. Now, imagine if cell phones were to operate on terahertz EM waves. I think sending messages or performing any simple task on the phone might take a few milliseconds, right?
With that being said, we are now almost at the end of our discussion of resonance. But before we conclude, I have a parting gift for everyone. Imagine a situation where everyone on Earth is asked to gather at a single place, and they are then asked to jump at a very specific frequency. What do you think would be the consequence of that? You can write it in the chat box. You can contact us later. It's up to you. And I'd like to conclude by saying that even though resonance is a very simple phenomenon to understand, it has immense day-to-day life applications. Thank you.
I don't see any real questions in the chat box, so I think we are good to move on. And I think that's only we have no questions only because of the how beautifully you explained the phenomena to us. I am actually glad that we understand physics of resonance right now, because that bridge video was really cool but also scary, and honestly much scarier than what CGI achieved in movies like Final Destination or The Dark Knight Rises. I would definitely not want to be stuck there in a car, and if you do, I think you might be a little crazy and need to go see a doctor. But jokes aside, you throughout the entirety of this event, one thing that we have consistently come back to is waves. Like from the beginning, when we were discussing about the experiments or the nature of lights or even black holes and grandfather paradox, and to the end, where you saw how small waves can create such large level destructions. Now, for our last presentation, the final of the day, we would like to call upon a group that is going to discuss about a wave that is very new, something we are still studying in our world. It is called the gravitational waves. I think you must have heard of it. And to further elaborate on this kind of wave, I'd like to call upon the final group of the day, Gravitationswellen.
Thank you, Soham. A very good evening to one and all present here. We are Gravitationswellen, and you are requested to strap in for a journey of 100 years. I am Proshmit, here to explain about the origins of the topic we have chosen, that is gravitational waves. Let's start at the very basics. There are a few types of waves in the world: the light wave, the sound wave, the drop a pebble in the water wave, and the Mexican wave. But the newest, and arguably the most amusing of them all, are gravitational waves. The saga begins in 1915 to 1916, when the famous German physicist Sir Albert Einstein published his paper on general relativity. In it were ideas that would revolutionize the way we think about the macroscopic world. His predecessor, Sir Isaac Newton, however, had envisioned a featureless and static universe. Newton's law of gravity had united the earthly physics of falling apples with the cosmic dances of planets and stars, but he famously refused to explain how it all happened. It fell upon Einstein to figure out gravity's true modus operandi. Gravity, as Einstein showed, did not just make what goes up always come down. Rather, gravity made the universe go around. In his theory, he argued that gravity isn't a force at all, but a curvature of time and space, soon to be christened as a unified term space-time, caused by mass and energy. Confused? Don't worry, as the German physicist was too initially. However, Einstein got help from mathematician Marcel Grossmann, an old friend of his, who introduced him to tensor analysis, using which the equations that explained his theory were laid down. Einstein was also ambivalent about the consequences of general relativity. In 1916, he raised the possibility of
gravitational radiation, waves rippling through space-time after a massive body abruptly changes its motion as in colliding with another mass. Einstein reasoned that such waves should exist because general relativity required gravity's influence to propagate at the speed of light, whereas Newton's gravity transmitted itself almost instantaneously. And there they were, the topic of contention that spread like wildfire from the Eastern European cities through the trenches and lines of firing squads, and finally into the Western world. As many scientists and historians rightfully claim, the war was simultaneously detrimental, horrific, enlightening for the science that was and that would be. Thus, it wasn't until the summer of 1974 that the first proof was found about gravitational waves. In the much celebrated Arecibo Radio Telescope in Puerto Rico, two astronomers, Joe Taylor and Russell Hulse, discovered a binary pulsar, the type of system that general relativity predicted would emit gravitational waves. They stress tested Einstein's audacious prediction, observing the change in the stars' orbits over a period of 8 years, only to conclude that the stars were getting closer precisely at the rate as if they would be emitting the gravitational waves. This was the first strike of the hammer on the nail. Meanwhile, a young physicist at MIT was chalking up the idea of the concept that would eventually solve this riddle. In 1972, Rainer Weiss proposed the optical method of detection of gravitational waves and finally convinced the NSF to grant the funds in 1979. However, there's one thing we need to clear up. The reason that gravitational waves are so hard to detect is because although the cosmic processes that create these waves are extremely destructive and violent, by the time they reach Earth, they are thousands and billions of times smaller. To put it into perspective, the waves reaching the Earth have a wavelength which is about 1,000 times smaller than the size of the nucleus of an atom. Now, Professor Weiss had to use the funds granted to him, and the way he spent that money will be elaborated by my friend Vinayak.
The construction for LIGO began in 1995 in Livingston and Hanford. LIGO exploits the physical properties of light and space to detect gravitational waves. In its simplest form, it consists of two 4-kilometer long and 1.2-meter wide L-shaped vacuum tubes which are covered by concrete shelters that protects the highly sensitive innards from the temperature variation, straight tectonic vibrations, and ambient light. Now a quick physics lesson. Interference is the phenomena where two waves, when in phase, superimpose to generate a resultant wave whose properties are the algebraic sum of the individual wave, and the scenario is called constructive interference. And when two waves are out of phase, they generate a resultant wave which is much less energetic than its constituent, which is destructive interference. And when multiple light waves interfere, they give rise to a band of alternating bright and dark strips called fringes. Now this is how LIGO operates. An emitter emits a laser beam that passes through the beam splitter that sends a part of the emitted light onto each arm. In the arm, the light first passes through the transparent side of the mirror near the beam splitter before it enters the vacuum cavity. Another mirror is placed at the far end of the arm, and they play ping pong with the light beam for about 300 times before it passes back to the photodetector that detects the fringe pattern after these two beams have interfered. This process increases the mean travel path for light and boosts its power, thereby leading to greater sensitivity to gravitational wave. Normally, the light beam destructively interfere and the resultant intensity graph is blank. However, when a wave passes through, LIGO sends a tweet to its scientist. Now, not to be left behind, the Europeans started working on the Virgo based on the same principle. What happened next, Dipro is here to tell you just that.
Well, Vinayak, it was in the year 2002 that LIGO was brought to life for initial launch. Observations during the initial LIGO era led over 100 publications of observational limits on the strength and frequency of occurrence of gravitational waves from broad range of commonly accepted gravitational wave sources. But without being able to detect any signs of gravitational waves, phase 2 was implemented, and it's like Iron Man take LIGO was upgraded to advanced LIGO, which was much more technically sounded than LIGO Mark 1, the higher octave. And this paid dividends. Within a year, gravitational waves from two black holes which collided 1.3 billion light years away were detected on September 14, 2015. And the announcement was made in 2016 after eliminating all other possibilities. The screenplay of the cosmic movie, A Pair of Black Holes, orbiting around each other and continuously losing energy through the emission of gravitational waves, causing them to gradually approach each other over billions of years. In the dying minutes, in the final fraction of a second, the two black holes collide at nearly half the speed of light to form a single massive black hole. A portion of the combined mass is converted to energy according to E equals to mc square, which is emitted as a final strong burst of gravitational wave. But how did LIGO detect this? Siddharth?
Thank you, Deepro. For this, you have to remember the structure of LIGO that Vinayak described. As it happens, when a gravitational wave passes through Earth, it squishes and stretches everything on it, including us. But being very minute, we humans don't feel it. But the light in LIGO's arm do. So much so that the two individual beams do not interfere destructively anymore. And a waveform is generated, which when computationally analyzed, describes the characteristics of the gravitational waves passing through and generates a waveform that produces the beautiful chirp of the universe. Now, the reason that we know that it was the collision of two black holes that caused the gravitational waves is because the LIGO-Virgo collaboration had extensively generated theoretically predicted waveforms for different scenarios. And when the waves were detected using a low latency search method, it was compared to the database, and the closest associated waveform pointed towards the collision of two black holes as being the culprit for the formation of the gravitational waves. Following this milestone in physics, the three masterminds behind LIGO, Rainer Weiss, Barry C. Barish, and Kip Thorne, along with the entire collaboration, were awarded the Nobel Prize in Physics in 2017. The future is quite open for this field of exploration, with the recent detection of the merging of two neutron stars creating quite a stir in the scientific community, as it was discovered that heavy metals like gold and platinum are created in such cosmic events. With interferometers in space set to join the effort very soon, physicists seek to detect events even more remote and exotic. Gravitational wave astronomy will positively affect our perception of the universe, being the years to what was predominantly observation by sight. With multiple collaborations set to join the effort in India, Japan, and Europe in the near future, the excitement is just simmering. It took 100 years to detect gravitational waves, but only the observable universe is the limit to the wonders that we'll detect in the next 100. I am Siddharth Datta, and I was joined by Proshmit Dashgupta, Vinayak Chakraborty, and Deepro Das, and we are Gravitation Sweden. Thank you very much.
Well, I don't see anything meaningful in the chat box and I don't even understand it anymore. So I'm just gonna skip that part. Okay, so that was a really interesting presentation, I must say. And I think it beautifully illustrates how in physics we are moving on with research, and yet the work from the past, the legacy of our work that has been done in long time ago is gaining legitimacy now. It is an interesting time in the world of physics right now, an exciting time in our worlds. We're at a point where a lot of avenues of research is opening up, a lot of new opportunities for every young mind trying to find answers to the universe. I think it was Frank Herbert who said something in 1968 about how deep inside the human consciousness, there is a pervasive need to find logic in a universe, when the universe is always one step beyond the logic. And I kind of agree to that. But still, we try, because that is all we can do. We show up, we do our part, we try to gain knowledge. We try to find meaning in this meaningless life. And through our pursuit, we gain the knowledge of the past and we try to leave something behind for the future. And I think everyone here today, all the presenters have done that. They have shared in their own way the unique knowledge that they wanted to share with you, and they shared it with passion they had for the subject. And so I'm really thankful to all of them. But more than them, I'm actually really thankful to all of you who listened to the end, because you are the ones who made this presentation worth it for us. Thank you. I thank all of you from the bottom of my heart. And now it is the end for me today. And I would like to call upon Pratyay Patra for the vote of thanks.
Hello, everyone. So, it's a great privilege for me to propose a vote of thanks to all the dignitaries present here. On behalf of the Heritage College, I'd like to thank the entire fraternity of the Kalyan Bharati Trust for giving us this opportunity to organize this webinar, and particularly me, Manos, and Vishal to mentor it. This webinar would not have been possible without the guidance of our Executive Director, Mr. Probir Roy, our Chief Executive Officer, Mr. Pradeep Kumar Agarwal, and Student Coordinator, Clayton M. Moses. From the core of my heart, I'd like to thank our beloved Principal, Dr. Pushpita Ranjan Bhattacharya, who is actually not present among us today, unfortunately, and Joint Registrar Kavita Shastri for their constant support and guidance. My sincere thanks to Professor in charge Amitava Ghosh and the head of the physics department, Dr. Madhubrata Bhattacharya, and all the other faculties and staff for constantly supporting us. Last but not the least, I'd like to thank all the viewers who gave the important time and have participated to make this event a great success. And with the hope that everyone stays safe and sound in these tough times, I'd like to conclude this webinar so everyone present here now may leave.